All right, class, welcome. So today we're going to dive deep into something really fascinating, something that's happening right now inside every single data center that powers our world. It's this hidden battle, this constant tug of war between getting things done incredibly fast and, well, not boiling the oceans with the energy it takes to do it.
So here's what we've got on the docket. First, we'll look at the core conflict. Then we'll talk about the two main ways engineers have tried to solve it, polling versus interrupts. After that, things get interesting. We'll see how a huge problem, the killer microseconds, popped up when things got too fast. And then, of course, we'll look at the clever solutions and wrap up with where we're headed next. Sound good? All right, let's jump right in. Section 1, the core conflict. So, everything we're talking about today, it all boils down to a really, really simple choice. A choice a computer has to make millions, maybe billions of times a second. And that choice is, how do I wait?
I mean, it sounds almost philosophical, right? But believe me, the answer to this question has enormous billion-dollar consequences. We're talking about what makes your Google search feel instant and also what contributes to the massive energy footprint of the entire internet. And really, it boils down to two fundamental approaches. Think of it like this. On one hand, you have polling. This is the little kid in the back seat on a road trip, right? Are we there yet? Are we there yet? Are we there yet? Constantly asking. On the other hand, you have an interrupt. That's like saying to the driver, you know what, wake me up when we get there, and then taking a nap. Two totally different ways of waiting. And you can probably guess the problem with that are we there yet method. As this quote from the Metronome paper points out, it's just a huge waste of energy. That CPU core is fully dedicated, it's spinning its wheels top speed, burning power, asking that same question over and over, even when absolutely nothing is happening. It's busy doing nothing. And we're not talking about a little bit of waste here. It's massive. See, to get that absolute split-second fastest response, what do data centers do? They basically tell their servers you are never allowed to sleep. They disable the power-saving modes. And the result, as this data shows, is that more than 65% of the potential power savings just vanish. Poof. All to keep those servers on high alert 24/7. Okay, so let's get a little more specific. Section 2 is all about these two paths. Polling versus interrupt. We've used the road trip analogy, now let's put some real computer science terms on them so we can really understand the trade-off that designers have been stuck with for decades. So first up, polling. This is the brute force way. The CPU is literally in a tight loop, just asking a device, like a network card, over and over and over, you got anything for me? How about now? Now? It's simple, and it's super fast, because the second something arrives, the CPU sees it. But the downside is huge. That CPU core is pegged at 100%, completely consumed, unable to do any other useful work. Then you've got the interrupt. This is the more civilized approach. The CPU can go off and do other work, maybe even take a nap in a low-power state. And when the network card finally has data, it sends a signal, an interrupt, that basically taps the CPU on the shoulder and says, hey, wake up, I've got something for you. It's way more efficient. But there's a catch. That wake-up process takes time. And this table just lays it all out perfectly. Look at the trade-offs. Polling gives you the absolute lowest latency, the fastest response time. But CPU usage, 100%. Power use, high. Interrupts are the mirror image, higher latency. But CPU usage is proportional to the load, and power use is low. This was the fundamental dilemma for a very long time. You had to pick one, speed or efficiency. You just couldn't have both. All right, section 3, the killer microseconds problem. Now, for years, that trade-off we just talked about, it was fine. People lived with it. But then something new came along, a technology called RDMA. And it made networks so ridiculously fast that suddenly that little bit of wake-up delay from an interrupt wasn't so little anymore. In fact, it became a massive bottleneck. So what is RDMA? The name stands for Remote Direct Memory Access, and it's basically like building a private teleportation tunnel directly between the memory of two computers. Data can just zap from one machine to another, completely bypassing the slow parts of the operating system. We're talking about transfer times of just a couple of microseconds. That's millions of a second. It's just an insane speed up. And here's where the problem really comes into focus. When your hardware is that fast, suddenly the time it takes to wake up a sleeping CPU isn't a small thing anymore. This quote from the Fast Wake paper says it all. Using an interrupt was suddenly 5 to 7 times slower than just polling. And that massive gap, that wasted potential, is what researchers started calling the killer microseconds. This chart just puts it in stark visual terms. Look at this.
With polling, you get that data in 1.6 microseconds, blazing fast. But if you try to be efficient and use an interrupt, the time skyrockets to over 10 microseconds. That huge gap between the blue bar and the red bar, that's the killer. It's almost 9 microseconds of just waiting. All that amazing speed from your fancy RDMA hardware, totally wasted.
So what's taking so long? Where does that delay come from? Well, the main culprit is this: waking up the right program. Imagine the interrupt arrives on one CPU core, let's say Core 1. But the program that needs the data is sleeping on Core 8. Core 1 has to basically send a little message over to Core 8 saying, hey, wake up your guy. And that communication between cores, it's just slow. 2 to 3 times slower than if everything happened on the same core. Okay, so things looked pretty bad. But a big problem like this killer microsecond thing, well, it often leads to really big, really smart solutions. So in Section 4, we're going to look at how engineers started forging these smarter, hybrid approaches to get the best of both worlds. So first, let's just break down that old, slow process. It's kind of a mess. A network packet arrives, the NIC sends an interrupt, but it goes to some random CPU core. That core then has to play detective, figure out which program the packet belongs to, and then send another message, an inter-processor interrupt, over to the correct core. Then that core's scheduler has to wake up the program. It's this long, convoluted chain of events that just burns through microsecond. Now look at the fast wake way. It's so much smarter. Step 1 is the genius part. Just make sure the interrupt goes to the correct core in the first place. By routing the signal intelligently from the start, you completely cut out that slow cross-core message passing. The kernel path is shorter, the thread wakes up directly. It's a much cleaner, much faster path. But what if you need to be even faster? What if you need that absolute rock-bottom latency? Well, FastWake has another trick up its sleeve. It can dedicate one core to act as a dispatcher. This dispatcher thread does the polling, but it does it on behalf of everyone. So instead of 10 programs all polling on 10 cores, you have one core polling for all 10. When data for one of them comes in, the dispatcher can wake it up super fast because it's all happening right there on the same core. And, this whole problem wasn't limited to just RDMA. Other popular high-performance networking frameworks like DPDK have the same issue. They're built on polling. So as this quote points out, you have these CPU cores that are just reserved, running at 100% utilization all the time. It doesn't matter if there's a flood of network traffic or just a tiny trickle. The power consumption is always maxed out. So the solution that the Metronome project came up with was to be adaptive, to be smarter. Instead of just polling constantly, it goes into this sort of intermittent sleep mode. It takes tiny little naps when things are quiet to save power, but it's designed to wake up in a flash the moment network traffic picks up. The end result? The CPU usage and the power draw actually matches the amount of work being done. What a concept, right? And that brings us to our final section. The future is adaptive. All of these solutions we've looked at, they're not just clever hacks. They actually point to a whole new way of thinking about building these kinds of systems.
So if there's one thing I want you to take away from this entire lecture, it's this. The future isn't about choosing polling or interrupts. It's about using polling and interrupts. That old, rigid choice, it's a false one. The smartest systems now don't pick a side. They are flexible, they are intelligent, and they use the best tool for the job at any given moment.
Ultimately, the real breakthrough here is in building these adaptive systems. Systems that can look at the traffic coming in and decide for themselves, okay, now it's time to poll. Or things are quiet, let's sleep and wait for an interrupt. And now that we've more or less figured out how to slay this particular dragon, it leaves us with a really exciting question to think about. As our world keeps demanding faster and faster data, where's the next killer microsecond hiding?